Alright, so at the top we have an example for each type. So you have your lower, which is kind of like your left, your upper, which is like your right, and then your M, which is your RAM. So here were the answers to all three of those with work. I'm going to flip down the lights so it's a little easier for you to see. Okay, and then number 2. So in number 2, the key piece of information was that it was 3 rectangles. So you use that to find your width or your delta x. And then you found your right endpoints, left endpoints, midpoints. And what you'll notice is down here, I just tried to make my life a little easier by writing out my table of values for the plots I pointed. Okay, at the top of the next page, number 3. Three and 4 are very similar to the wording you would see on an AP exam. They're going to typically give you a table of values and have you find a Riemann sum from that. Now what I've found is the AP exam table of values are not usually as nice as some of these table of values. Okay? Any questions on... Go ahead, honey. On the test, you're going to see an example a lot more like number 5. Like, if I were to give you a question, I wouldn't put it up to interpretation. It would be something like number 5 where you have a table of values. And like I mentioned, typically the table of values aren't going to be even intervals. So I would probably give you a table of values where it's like 0 to 1, 1 to 3. So like 1's a width of 1, 1's a width of 2. So that I know that you understand kind of how the different widths affect and which endpoints to pick. Does... What, honey?
What is the 6 times?
I think it got typo. Like, I think the graph got smushed when I printed it. Like, it was 136. Like, I think the way Microsoft Word, this used to be in a doc, and I converted all of my documents over the summer to docx. And I think when I converted all my documents, some of my, like, spacings got goofed up. And I think that's what, and I didn't realize it happened on my table till after I had made all of your copies. Like even how number 8 like got put down at the bottom. And I don't know if I fixed it. Like sometimes I fix them and sometimes I just don't recognize it till after the photocopies go out. So if your numbers were off because you treated it like a 13 and a 36, sorry. And then apparently I skipped part A. I can do that real quick, but I don't know why I did that. Here's part B. And then 8. So for number 8, that was kind of like the different interval setup. So in number 8, they specified that you needed to have a set of intervals that were 3 sub-intervals of equal length. So your total distance was 6, and 3 sub-intervals made them sets of 2. So we actually skipped values on my table when setting up our rectangles. So like you can see, I sort of drew my rectangle from here to there, and if I'm using the midpoint, then I'm picking the value in the middle to get my height from. If it was a left or right, then you would still just pick the far or the far, depending on where that rectangle was. Okay, and then 9 was a trapezoid. So 1/2 height, base 1 plus base 2 plus base 3 plus base 4, where your outsides are single and your insides are doubled because the trapezoid heights at those 2 points would repeat when we make our trapezoid. So it's that 1/2 times 2, and then 4, and then 2 times the middle, 2 times the middle, and then 12. I'm pretty sure number 9 came off a past AP exam. I can't remember what year, but a lot of times when I gave you multiple choice problems on a worksheet or handout, I found them from an AP resource. Which I have some AP practice books if anybody wants to sign one out and borrow it because you want to start studying on your own. I also have some AP practice books. And are we okay with number 9? Number 10. Number 10, I kind of decided you could do this one of 2 ways. So the first way was to use kind of your trapezoids again. And you can see I kind of drew in my trapezoids because you were only going from 10 to 20. So like the points at 0 and 5 meant nothing. So that was using 2 trapezoids of smaller width. And then you had to add back to that the 60 from the initial. And then the other method, similarly to the first method, actually gets you to the 82. And again, you'll notice you get the 87 or the 82 and the closest value to those is 82. I'll zoom in a little more. Okay? So everybody feel pretty good about Riemann sums? Like I said, you're pretty much guaranteed a question on the AP exam and a free response with a Riemann sum. I haven't looked at the mock exam we're taking in a week or two, but I'm going to assume the mock exam will probably have one as well. So it's something we'll continue to practice, look at, and study so that you can earn those points. So you have your new notes packet for today. Like I said, I'm going to pause on going over last night's textbook homework because I did kind of tell Quickie he could have till Monday, and I'd postpone going over till Monday since he was really in a lot of pain. So let's move into 5-3. So go ahead and look at the graph on that front page. Go ahead and read over it and see what you think. And then we'll talk about it. Alright, so like I said, we've moved into integration. Integration is the second half of calculus, and we have explored area under a curve. So we're going to spend the next couple weeks and months looking at area under the curve, and we talked about its notation. So understanding notation is a really important part of understanding calculus. So the notation for this is read as the definite. So this is a definite integral. And I can't remember, in physics, do you guys do definite or indefinite? You have definites? Okay. So this is a definite integral, and we read it as from A to B of f of x with respect to x. And what that means is we are using that integral to find what we call the net area bounded by the x-axis. So it's bounded by the x-axis and the curve between vertical lines A and B. So it's the net area bounded by the x-axis and the curve. As well as vertical lines A and B. And we already previously went over the parts of the integral, but the integral itself is the symbol. B is the upper, A is the lower, and those are the upper and lower limits of integration. So just like calculus starts with limits, so does integration. F of x is called the integrand, so it's the grand part of the integral. And the variable here is our variable of integration. Okay, so in our notes packet, actually from yesterday, there was a page we didn't go over. So that page was a relation between the limit and the Riemann sum. So that page was a relation between a limit and a Riemann sum. So what I want to do is kind of give you this idea or summary here. About that relation. So a Riemann sum is a limit as n approaches 0 where you have f of x and delta x. An integral is a to b, and we can use n-int, but we want to come up with a relationship that relates the integral to the Riemann sum. And the reason we want to do that is because we want to be able to compare those two values to one another. Or there's typically an AP question that relates them. So what we're going to do is talk about how the parts of the Riemann sum relate to the parts of a definite integral. So down at the bottom of that worksheet, what I'm going to do is kind of give you a summary of how to go from each of these two forms to the form of a Riemann sum. Okay, so let's go back to, let me get back to my document camera. There's my pen. Okay. So down in the bottom of that page, in the space left for you, let's first talk about the relationship of the Riemann sum equation and the integral equation. The Riemann sum, or the delta x, is equal to b minus a over n. Well, that's hard to see. Let me see colors. Which in the Riemann sum limit becomes 1 over n if the distance between b and a is 1. So if it's not, this is kind of representative of like my dx in a way. So it's kind of like dx over n. And we're going to talk about how that works into our formula. So the Riemann sum is going to become f of a plus delta x times I times delta x. So the delta x almost repeats in our problem. The delta x comes from the values of the integral. That's where the b minus a are coming from. So these b minus a's are coming from your integral b minus a. So in example number 1, b minus a would be 6. So if you were up here and you're looking at example number 1, your delta x in the Riemann sum equation would be 6 minus 0 over n, or 6 over n. So when I go to write that as a Riemann sum, that represents my delta x. The Riemann sum limit never changes. So it's always going to start as the limit as n goes to infinity with the e, n on top, I equals 1 on bottom. That part of the Riemann sum never changes. Down here, it's the function. So the function of this is the square root. So the limit will have the square root. And then it's f of a plus delta xi. So that a on delta xi is this delta x here, going in for x here. So it's going to be 2, 6 over n plus 1. So that delta x is going in for my variable. And it's representative of the dx at the end of the integral. So this is also all multiplied by 6 over n. Let's do another one. These are typically multiple choice. So if you can get the idea of what your delta x is, you can typically find the correct multiple choice. So it would be delta x equals 3 minus a minus 2 all over n. So we get 5 over n. So it's the limit as n goes to infinity of the summation from n to I. The function this time is x squared. Now remember how I told you that it involves a? Where else do we see a? A is my lower limit. So in the previous example, my lower limit was 0, so it didn't affect my problem. Now my lower limit is negative 2. So when I plug in my x for f of x using that a plus delta xi, it's going to be negative 2 plus my delta x, which is 5 over n. Hey guys, I'm sorry, I forgot my I in that first example up there. There should have been an I on my 6, I'm sorry. And that would be negative 2, because that's my a, plus delta x, my 5 over n, times I. It's plugged into the equation, which is x squared, so you have a squared. There's no x on the 3, so it's just minus 3. And then all times my delta x again, which is 5 over n. Okay, one more. Delta x, upper minus lower, so we get another 5 over n. Limit as n goes to infinity, summation plug in a plus delta xi, so you get 3 1 plus 5I over n minus 4 multiplied by delta x. And again, once you do like 1 or 2, now that we've done the third one, it's like, okay, I see it, I feel it. It's the limit down here as n goes to infinity, n I equals 1, f of a plus delta x times I times delta x. That is the Riemann sum. So this represents the Riemann sum as an integral. Could you do the reverse? What if I gave you the Riemann sum and asked you to find the integral? If I gave you a Riemann sum, could you write it as an integral? Would you like to try one? You know it. Okay, so we're not going to do 7 and 8. We'll just use that space. So what if I gave you the limit as n approaches infinity of the summation from I to 1 of n, and let's say that it was a 3, and then inside it is -1 plus I over n. Sorry. Let's go with 2I over n. I'll make it easier. Cubed times 2 over n. Okay, what's my lower bound? What's my lower bound? What's my a? Yeah. My a is -1, right? Because this is a. That's the a of my integral. If b minus a is equal to 2, what does that make b? If b minus a is equal to 2, and I know a is -1, what's that make my b? So b plus 1 has to equal 2, therefore b has to be 1. What's my function? Yeah, 3x cubed. And then that 2n represents dx, because you always have to have a variable of integration. Good. So you can go forwards and backwards now. Anybody still unsure of looking at the Riemann sum as a limit? Okay, I promise you that's the hardest part of today's lesson. That's the hardest part of today's lesson. The rest, I feel like you're actually going to really like today's lesson, because it's like do you remember like the first day of derivatives when we did like our power rule and you're like, yes, derivatives are easy? That's kind of like today for integration. You want to give me that like, yes, this is easy. Or maybe you want to give me nothing and you just want to be quiet all day. And I'll just sit back here and talk all cheerfully by myself. Okay? Let's do this